All right. I've got a few more equations to throw at you that are necessary as we get into cycles. And so there's two things going on here, two big assumptions. Ideal gas, okay, and in this class pretty much every time, I couldn't think of an exception. I think pretty much we're always going to assume any gas is an ideal gas. So, but we're ideal gas and isentropic process. And before you say, oh, that'll never happen, isentropic, that doesn't happen, remember that you can get pretty close to isentropic because stuff can. So you might gain entropy because of friction and things like that, but you can lose entropy due to heat. So it's not a crazy assumption. Isentropic is not a crazy assumption. Okay. So when you have isentropic process with an ideal gas, which we're going to model the internal combustion engine as such, by the way. Okay. We're going to model the internal combustion engine as an isentropic ideal gas process. You have the following three property relations, okay? These actually can be derived from the stuff we did before, but I just didn't think it's worth our time to go through and show each one or whatever, but you can. One thing to recall, though, is K here is what we call the specific heat ratio. It's C sub P over C sub V. And that's a good reminder because if you see these equations on your equation sheet, when you see those K's in there, you go, oh, well, that has to be only for gases, okay? Because there's really no such thing as a K. I mean, technically, I guess there is, but there's really no such thing as a K for liquids and solids and things like that. And the only K that you really, most likely are going to need to know is K equals 1.4 for air, okay? So for air, it has a specific heat ratio of 1.4, C sub P over C sub V. But you can use that and those property relations for isentropic processes, okay? If you look at Chapter 7, you'll notice there's probably 50, 60 different equations. I'm trying to boil it down to critical, simple concepts, okay? We're going to assume gases are ideal, we're going to use specific heats, or we're going to use the tables, okay? If you look at I took out a lot of stuff in Chapter 7. The reason I did is because it just makes it more complicated, and I'm really trying to simplify this as much as I can. Okay? So I took out a lot of stuff to keep it to the bare bones minimum. This is what you need to know. Okay? These are the relationships you need to know. Now, there's a couple more relations that are important as well, and that is dealing with this concept of relative pressure or relative specific volume. Now, remember this. Remember when we brought up these air tables? Let me bring them up again. Let's go to the air tables, if I can get to them. Okay. Not there yet. Let me get down. Almost there. Okay, here it is. Ideal gas properties of air. And remember, as we looked at these things, that if you know the temperature, you can easily get the enthalpy H or the internal energy U. But I said you can't easily get the pressure and the specific volume. Notice that they give you this PR and VR. That's relative pressure, relative specific volume. There's not even any units on that. Okay, that kind of gives you a little, scratch your head, right? There's not even any units on that, on PR and VR, okay? And I said that, and this is something to remember, okay, is that when you have air or any other gas, and you need to get the pressure or the specific volume, you really only got one thing, and that's the ideal gas equation, okay? In fact, I almost want to kind of have you do it as a reflex. Whenever you see a problem dealing with a gas, air, helium, whatever, okay, mostly air, I almost want you to just reflex and write the ideal gas equation, okay? And then if it doesn't have a gas, like steam, liquid water, other stuff, right? I almost want you to reflex and say, this is not ideal gas equation, okay? We don't want to use it on liquid water or even steam because you got tables, okay? But anyway, PR and VR, there's no units there. How do you even use that? I did see some students, because we had a quiz a few weeks ago, which, by the way, I'll hand back your quizzes next week. We had a quizzes a few weeks ago, or after spring break. And some people even tried to pull out this PR and VR because they didn't know what to do. They're like, I'm going to pull out a PR and a VR. I don't even know what that is, but I think it's pressure, right? Well, not exactly. But here's how we use it. This is nice. When we have isentropic ideal gas process, we can say P2 over P1 is equal to the relative pressure 2 over the relative pressure 1. And we can say V2 over V1 is equal to the relative specific volume divided by 2 divided by the relative specific volume at 1. Okay? No memorization here. All these equations will be provided for you. Okay? No memorization. Okay? But you need to know how to use them. Okay? The mental cue is when you see K's, you need to think gases because K is C sub P over C sub V. In fact, I'll even put that on your equation sheet too. And the other mental cue is when you see this PR and VR stuff, you go, oh, that's from that table, and I didn't know what that was. Okay? So we've got some different connections. And again, the reason I'm bringing these up is when we analyze the internal combustion engine, you're going to need to know this stuff. By the way, this one here, V2 over V1, or V1 over V2, okay? Most likely it'd probably be more like V1 over V2. It depends on how you define V1 or V2. Is what we would typically call the compression ratio. Okay? The compression ratio, any of you who are gearheads, get into engines, things like that, you know that compression ratios that's an important parameter, an important property of an engine, okay? It's compression ratio, all right? And so I'm kind of giving you a preview of what we're going to do in a few weeks when we get into the internal combustion engine, whether it's spark ignition or compression ignition, which we'll get into both, diesel or regular. We'll get into both. And that's going to be an important relationship. Okay, so we'll get there in a few weeks and we'll really get into this. So, just pressure. It's a process, right? It's just so you have a before and an after, right? State 1, state 2. So that ratio, that's all that is. Okay, I think everything here will become clearer when we do this example, okay? So, yeah, question?
Can K ever be less than 1?
No. No, you can prove that C sub P is always going to be greater than or equal to C sub V. So the ratio has to be greater than 1. Yeah? Well, you can plug in, see the PR and VR here that I've circled in red here, and the values that correspond on the table. That's when you can plug them into that equation. You can plug in PR and VR here in that equation to get P2 over P1. No, yeah, no. Yeah, don't do that. Don't take ideal gas and just say, oh, I don't know the pressure. Let me just throw a PR in there. No. Yeah, no, they can't do that, okay? In fact, these two columns, PR and VR, have very limited uses, okay? Don't use them unless you're going to do them as a ratio in this type of equation. That's it. Never put them in by themselves. They're useless by themselves. They're only useful as a ratio because, think about it, they're dimensionless. How could a dimensionless number be used in a lot of these calculations? I mean, for pressure, that doesn't, no, you can't do that. It's only as a ratio, okay? But that's a good question. And a very good caveat. Okay, I think this will become clear when we look at this example. All right, and I have this example here. You're asked to demonstrate the auto ignition of paper under high pressure. You wish to design a device that will create air at a temperature of 300 degrees Celsius to light paper. It takes somewhat around 300 degrees Celsius to light paper. Okay? So we got that. And so what we're saying here is that I want that my temperature 2 to be 300 degrees Celsius, which is, by the way, 573 Kelvin, right? Because remember, most of these things here, We have to get this in Kelvin, okay? So I have an example here, and what I have here is a Otto is a compression igniter. I have a picture of it as well. So those of you who are watching this go, oh, what is this thing I'm holding? That, okay? And so this is a compression igniter, and what you see there is a nice, beautiful flame that comes from the compression igniter, but it doesn't always work as nicely as that, as you'll see here. But if you'd like to try to light this paper on fire, we'll see if you can. But that's what I have, and I'm going to pass it around now. And what's that?
Flash cotton.
Flash cotton. Now I would imagine. If you'd like to see if you can light this sucker on fire, don't press too hard. But you should be able to see the flames a little bit of smoke, and you should definitely see that it gets hot as you do it. But you may not be able to get a full flame. And whoever does get a full flame, if it ever does happen, then no one else is going to be able to see it. So if you can't get it after a few times, pass it, because we got to keep moving. So, but here's what we're going to assume. What do you want to assume as the initial temperature? The temperature before we started this whole deal. What do you think would be a good air temperature to assume? Room temperature, right? Right? Before I brought this in, the air was probably about room temperature. How about we say it started out at about 27 degrees Celsius? I like that because then that's 300 K, right? Okay? So I need to get 573 K. I'm starting out with air pretty much room temperature 300 K. I'm going to design this compression igniter, just like you see, okay? To do that, I've got to figure out what's the compression ratio I need. By the way, those of you who look at that thing, what do you think is the compression ratio? If you held that thing all the way up at the top and you pushed it all the way near the bottom, what do you think the compression ratio would be? I'm guessing maybe 30?
More than 5.
More than 5, yeah. So, yeah, quite a bit, yeah. So, I don't know, but, yeah, it's hard to light those things. Anyway, okay, it's quite a bit. It's quite a bit of a compression ratio. So, let's try this. Let's try this. How are we going to solve this? Magic. We're going to apply these equations here, okay? We're going to assume air is an ideal gas, and we're going to assume it's an isentropic process, and I want to solve for the compression ratio V1 over V2. Okay, that's the compression ratio. So okay, that's okay. Let's not pass that around anymore. Then let's just pass it and observe now. Okay, just pass it and observe. Okay, all right.
That's why we can nice things.
Yeah. Okay, take a look at what I'm trying to solve for. V1 over V2, right? Let's take a look at my equations above. You see an equation that I can use up at the top here? Maybe this one, right? Because I have the temperatures, and I need to use the temperatures to solve the compression ratio, V1 over V2. So let's do this. Let's use that. Let's say this. The temperatures, T2 over T1, according to that equation above, equals the compression ratio to the K minus 1 power. Right? What that says, if you fill in the numbers, is that my T2, my desired temperature, is 573 K. My T1 is my initial temperature, 300 K. Right? That's going to equal my compression ratio, V1 over V2, to the K minus 1 power. Remember what K is? For air, K is 1.4. So 1.4 minus 1 is 0.4. Okay? Now, I cannot solve for V1 or V2. I can only solve for V1 divided by V2 here. Okay? So how would I solve this? How would I solve for V1 divided by V2? Anybody? Yeah, or take it to the 1 divided by, you could do this. It would be 573 over 300, and you could take it to the 1 over zero point 0.4 root, right? Which, by the way, 0.4 is 2/5, right? 0.4 is 2 over 5, right? So wouldn't that be 5/2 root? So wouldn't this be the same thing as 573 over 300 to the 5/2 root, if you want to get to it? And if you do that, you should get 5.04. Okay?
Now, is there a table or something you can look up if there wasn't error that some other kind has to find a K?
Oh, yeah, for the K, because that's the only thing that's unique to this. Yeah, Ks are in the tables. If you go back to your tabular data, in fact, let me just show you this. Ks are in the tables. Okay, let me pull this up real quick. Oops, I already have the tables. Place this up right here. Ks are in the tables. Let me show you. Look, there's air has a bunch of Ks. We assume it's 1.4, but notice the air Ks for air change a little bit. You got a bunch here. You got all sorts of things. You always got the Ks. The Ks are available to you. It's the last line in the column there. So you got the Ks. All right? So it's a good question. All right. Now, there's another way to do this. We assumed, what we did was we assumed isentropic ideal gas and used the relationship at the top. We could also use the tables and use those either reduced pressures or reduced specific volumes. Okay? In particular, what I would suggest we use is the second equation I have marked in green, the one on the right, because it says V2 over V1 is equal to VR2 over VR1. Okay? Well, you could also write this as such, right? You could also write that second equation as V1 over V2 is equal to VR1 over VR2, right? Same thing. I just flipped it, right? Same thing. Nothing controversial there. Okay, so how does that help us? Well, what you could do is you could actually get VR1 in the tables. Okay? How do I get that? Well, what's T1? T1 is the initial temperature of the air. That's going to be a T1 of 300 Kelvin. So you go back to your tables. You go back to your tables for air. Got to go back to my air table here. Here we go. 300 Kelvin. 300 Kelvin. My VR is 621.2. So for 300 Kelvin, I look up a VR of 621.2. Okay, so I put that in there. Okay. There's no units. And then you got VR2. That's also going to come from the tables at a temperature T2 of 573, right? That's my final temperature, 573 K. Now, this one's not exactly on the tables, of course. We really have to interpolate this one to get 573. If you look at 570, 570 corresponds to 121.2, and 580 corresponds to 115.7. 580 is 115.7. 570 is 121.2. So you really do have to interpolate. I will tell you, if you do interpolate, you get awfully darn close to 120. So interpolate, and you get 120. Okay? Therefore, if I want to find out, in this particular example, what is V1 over V2, I can say, oh, it's the same thing as VR1 over VR2, the relative specific volumes. Then I can say, oh, that's just 621.2 divided by 120, and I get 5.18. You'll notice it's slightly different. pretty close. Why is it different? Because you're using tabular data. You're using some tabular data. You're not just doing a quick property relation.
Say I wanted to mix butane and air since they're both gases. How would you include the pressure ratio since it's two separate gases?
Yeah, you got partial pressures then, and that's a little bit more complicated. We'll get into that right near the end of the semester. Last week, we won't do butane, but when we do partial pressures, what we do at the end of the semester, the last week, is we realize that air really isn't just air. It has water in it, right? Air has water vapor, and so really you have the total air pressure is the pressure of the air plus the pressure of the vapor, water vapor. So you've got some mixes going on. We'll get into that the last week, because air isn't true. We'll deal with dry air. We'll assume air is dry up until the last week of the semester. Then we'll say, oh, by the way, it's not really dry. It has water in it. So we'll do that. Yeah. Oh, by the way, and then we're done. See you later. Go on and do some more stuff. Okay. Let's talk about here reversible work. Okay. I expect everybody to know, to be able to finish that sentence. Work is equal to what integral? V dV. We should almost do like, start the day, everybody, work is equal to the integral V dV. Yes, good. We should know that one. I don't ask you to memorize much, but I tell you I want you to memorize that one. Okay? Very few other things. Though honestly, I think I still put it on the equation sheet. Okay, whatever. All right, but I still want you to memorize it. So, yeah, regular volume. Okay, but we have a few relationships that we can use. I'm going to make this kind of a little side note here, because I'm not going to go through a rigorous demonstration, but we'll kind of show you basic how to put it together. You can write the first law of thermodynamics for control volumes as this. Q, differential Q minus differential W is equal to, it's not really this, different DH is equal to DH. Okay, that's just Q minus W is equal to H, but we're differential, right? Then we can say this for differential heat is equal to TdS, and if you don't know where that comes from, see prior lecture. And then we can also say from prior work that TdS is equal to dH minus V dP. Okay, I'm going to kind of leave that as a side note. And if you want to see how it all goes, I challenge you to do the substitutions because it's pretty darn simple. You can basically use all of that to prove a very interesting relationship for what we call reversible work. Work reversible in. Now I'm going to call it in because that makes this a positive number. If I were to say it was out, this would actually be a negative number, and I want to keep it simple. So we're going to say work reversible in is equal to, it's kind of an interesting equation, V dP. That's specific volume.
So the one where it's also specific volume off to the side.
Yeah, that is, yeah. Yeah, specific volume. Okay. So what is this saying? First, before we look at this, because it looks like all I did is played a little algebra and said, oh, look, I have work equals integral P dV, but now work is equal to integral V dP. Okay, that's kind of weird. They look kind of similar. Here's what we're saying. Reversible work means the minimum amount of work. Okay, the minimum work. Okay, that's like the minimum work. Okay, whereas my blue equation says work equals integral P dV. That's kind of fundamental. Okay, this is the minimum work. The minimum work in. Okay, so let's say we have a device that requires work in. Remember, devices that require work in are things that we have to plug into the wall typically, right? And so I'm going to give you a couple of good examples that I think make this the reason why we talk about it. I want to think about pumps and air compressors, okay? Pumps and compressors. Basically, pumps and compressors do the same thing. They raise the pressure of the fluid that's in them. Okay? Right? Now, in this class, I'm always going to call a pump something that deals with a liquid. Okay? And in this class, I'm always going to call a compressor something that deals with a gas. Okay? So pumps, the purpose of a pump is to change the pressure of the liquid to a higher pressure, to raise the pressure of a liquid. The purpose of a compressor is to raise the pressure of the gas. Okay? Now, this is why this is so interesting an equation, and it helps connect some very fundamental concepts here. The integral of the specific volume times the pressure change, essentially, okay, dP, is equal to the reversible work in. Now, I said pumps handle liquids and compressors handle gases, right? Okay? Which one, think about this for a second, make sure you know, which one of those has liquids and gases? Which one has a very high specific volume and which one has a very low specific volume? Gases have a high specific. So, which one is going to be easier to operate? Is a pump pumping a liquid to a higher pressure, or is it a compressor pumping a gas to a higher pressure? If it's integral VdP, which one's going to have the greater work in, meaning it's going to consume more energy? Yes. You see that? What this is saying is something that you probably knew all along. To pump a gas to a higher pressure because gases have a much greater specific volume. Okay? Just think about two different things in your mind. Think about a liquid pump. I don't know, most people around here don't have basements, so most people don't have sub pumps, okay? But if you had a sub pump, a lot of those things run off batteries, okay? You realize that? Now, why is that? Because they don't take a lot of power. Liquid pumps don't require a lot of power, okay? But have you ever seen an air compressor run off a battery? I've never in my whole life. Because that is almost impossible. Because air compressors, they're loud, right? Why? Because they take so much energy, right? Because they're really working hard to compress air and to pump it to a higher pressure. To do the same thing with water would be super easy. Way less. So that's interesting. That's the one tidbit that's interesting. The other tidbit that makes that interesting is that whole deal right there is why steam power plants work. Because what you're doing with a steam power plant is basically it's a cycle, okay? And we're going to get into the steam power plant cycle after spring break, okay? But there's two parts to a steam power plant cycle that are really important. There's the turbine and there's the pump, okay? The turbine gets work out of the steam, okay? If you want to get the most work out of the steam, you want that V to be big, okay? You want that V to be big. You want steam. You want the reason why we have to do this with power plants, in power plants, we have to, when we use pumps in power plants, we have to make them liquid. So what we have to do when it comes out of a turbine is we have to then condense all of that water back into liquid form so that we can pump it up to a higher pressure again. And when we pump it up to a higher pressure, then we can heat it, turn it back into steam, and then do it again. Okay? And that equation gives us a really good insight why. Okay? You know, you have hand pumps that you can pump liquids with. You know, anybody used a hand crank to pump a liquid? Right? Have you ever done that with air? I don't think that'd be, I mean, obviously you could compress a little bit of air like that. So, but, yeah, you could do that, but how much air you have, and not very much. Think about it, yeah, you can do a little bit, you're right. You can do that with a little hand pump for air. But it's And the relative pressure is pretty darn small. So, yeah.
Because like filled out water would be a lot harder.
Oh, I know. Yeah, I know what you're saying. You're saying yeah, it's so much harder to pump. But the thing is that's because water is incompressible. See, the thing is, the reason why it is hard to do something like this. Oh my gosh, it's totally broken. So.
That's what I did.
Okay, it's okay. I have a replacement one. So I have a replacement tube inside, and I'll just give it to my student and he'll clean it up. So my student worker. So what's that?
That's fine.
Yeah, I know. He'll have to be careful.
Well,
So
like, if
yeah. All right. Okay, let's move on. Let's not worry about that. Okay. Here's another thing that's interesting. Remember when I said pumps always refer to liquid. If I want to get the pump work, we're going to use this equation a few times. If I want to get the pump work, I'm going to assume it is equal to V P2 minus P1. Very simply, why? Here's why. If I'm going to say my minimum work is equal to V dP, I'm assuming that liquid water does not change its specific volume, so that pulls out of the integral. So it's just this, right? And of course, that is equal to P2 minus P1.
So it's going to look a little different for gas.
Yeah, you couldn't do that for gas. That equation only works, that I have marked in blue, only works for liquids. Because remember, I say a pump, I'm always saying it's a liquid. Okay? If it's a pump, I'm saying it's a liquid.
Why doesn't it work for my gas?
Because specific volume could change, so you can't just integrate that. Yeah. Gases are compressible. And see, that's what's really happening with this compressing igniter, is that you're compressing the gas. You're changing. You can't do that with water. And the thing is, you can increase the pressure of the water dramatically, but you can't see pressure. How do you see that pressure? When you push, if you had water in the compression igniter chamber and you push down, you would be changing its pressure greatly. In fact, how could I observe that? I could make a little nozzle, and I could, and this could be used to squirt water at a high pressure, right? So I can change the pressure quite a bit easily, but you can't see pressure. So all what you're seeing, how easy it is because you're compressing the air. Okay. So some really interesting implications there. That pump work equation we're going to use when we do steam power plants. Okay, and it's really interesting implications we get from understanding reversible work.